Thank you. Well, I think I will stand here so that I can see the screen and the clock as well, which is also here. Now, here is a slide from a document that started off in 1984. It's an HCRP document, and there have been several documents since then with the same diagram in it. This is explaining that if you have 4 sensitive subgroups of individuals, or sensitive, average, or representative, I suppose you'd say, and resistant, then you have a spectrum of curves here for the amount of injury in the tissues, which Wolfgang described. If you then set a level for the injury which is observable, and say here, and you plot the incidence of that in each of the groups of individuals, then you have that one coming up to here, that one coming up to here, that one to there, and that one to there, like that. And the sum of all of those is the sigmoid curve that you see at the top. So that you can see that the threshold dose which you need is governed really by the sensitive individuals, which actually helps the resistant individuals as well. And if you look in publication 118, you will see a list of threshold doses, and I've put there for skin, for cataract, and cardiovascular disease. It states about half a gray for acute exposures or chronic exposures. And the squiggle here, here, and here, squiggle here, here, and here, means about. And the reason is that it's very uncertain if it is half a gray or if it is less than half a gray, because when you get under half a gray, the errors are larger, so that you don't know exactly where you are for that specified dose. And the question is, why would the threshold dose be independent of fractionation or dose rate at those low doses? So here's the linear quadratic curve in green, and if you're at low doses, then you are dealing with the alpha component only, which may be fixed or even declining, as some people think. And below half a gray, there are these larger error bars, but it is explainable, and you can also say, are there different target cell populations at risk for low dose and high dose for the heart and for stroke, etc. Now, for the A-bombs, it is an excellent data set for this sort of exercise. In the red box there, in the middle at the top, you see the curve of excess relative risk versus dose, and there's a dashed line for the first follow-up period and a solid line for the later period. So for the early one, you can see that there is a threshold dose of around half a gray, which I've mentioned already, there and there. But for the later period, it is more linear. And that explains basically why the dose limits for cataract are going lower and lower, and why for heart disease, etc., that something is happening at half a gray or less if you have these extremely long follow-ups for the life of the individuals. Now, in a large meta-analysis of 10 studies here, medical, occupational, ABOMs, etc., at low doses, assuming L and T and 5 years latency and a constant ERR after that, the excess risks were about 5% per sievert, which is of the same order as it was for a cancer risk in those same studies. So here it shows you that there is some importance of these effects for risk. I mentioned just that the risk is higher in children, and that's an aspect that will be covered later on. And the question is arising, is there a stochastic component to these late reactions? And I think the next speaker will also be speaking about that. But there isn't a lot of evidence about that. There are, for example, statements like this, which I'm showing, that because of the exponential decline here, that sort of implies that there may be a random statistical component, but if you're only in the first log, then it's hard to see if the data are really fitting an exponential better than a linear term. There's also evidence that I was involved in looking at reactions on the skin of patients with a reaction left and right, and is there a correlation? Well, there was, but there was also some unexplained variability, which we thought was a stochastic component. So it isn't all or none, it's some of that, you see. Now, also, from experimental evidence, it's obvious now, I think, that the effects at low dose may be different from the effects at high dose, and also the effects are different in different vascular components. And if you irradiate a whole body rather than local irradiation on the heart, you also have extra effects appearing. Now, in experimental animals, there are mice like these ApoE that Wolfgang has worked on, and even at these extremely low doses of 0.2 gray, they are picking up some abnormalities. So here's an experimental system for looking at that. There was a large report in 2010 from the HPA, and in the middle there, my time is up, it states that we do not think that the available evidence justifies consideration of a stochastic component as being established, although it remains as a possibility. And last of all, I think I'm up only a few seconds over, which for me is amazing. There is a large Euratom project which has been funded on the epidemiology and the modeling and the experimental data, which might help sort out some of these low-dose problems. Thank you. Thank you.